So let's look a little more at equipotentials because this is a very important topic that we're going to use a lot. And again, it's typically the easiest thing to draw yourself. So we're going to start here connecting equipotentials to the electric field itself. Later on in chapter 26, we're going to do this in a more quantitative way, but I want to show you this now since this connection is really one of the most important things to get out of this chapter. Your field lines, these magenta electric field lines, are perpendicular to your equipotential. You can see that here, that this is a right angle, but that's not just true in this scenario. This is always true. So if I give you electric field lines, you should be able to draw the equipotentials just by making sure that you're drawing it perpendicular to the field lines at all points. This will be a little more clear as we meet the electric potential from additional objects. Something else to know is that equipotentials never cross. And the reason for that is that every point in space actually has its own electric potential. Note that again here we've shown equal spacing. This goes from 0 to 0.3, 0.6, 0.9, 1.2. So if somehow these crossed, at that point, would that have 0.9 or 1.2? It doesn't make sense to have two different values. There will be some symmetries where you might have lines cross, but that would only happen if they both have the same value. For instance, if this is 10 volts and this line is 10 volts, well, it is actually okay for them to cross, since at that point in space, it's really clear that it still has 10 volts. So that's the only exception to that rule. They can only cross if they have the same value, and that rarely happens. The last thing to notice is that your field lines are going from higher to lower equipotentials. So our fields start at positive, which was 1.5, and are heading towards the negative, which is 0. And soon we'll be talking about the importance or the unimportance of defining 0. So the field lines point from positive electric potential to lower electric potential. So if I say higher or lower equipotentials, that just means the value, and note that I could start going negative and that would be even lower. So briefly, what is our source of potential? We've said that there is one, and we've talked about electric field, but again, in the real world, we don't normally talk about electric field. We actually talk about voltage and electric potential. And the reason for that is that batteries can create a potential difference. If I have two planes of a capacitor and I put a battery in between them, note that batteries have units of volts on them. And so that battery actually forces these two planes of the capacitor to be at a potential difference, right? The delta V between these, so delta VC in our notation, is 1.5 volts. How does that happen? Well, we know that we then get a uniform electric field. How do we get a uniform electric field? We get a charge difference. So what's interesting is that by putting a battery here, we would actually start with electric potential, causing that potential difference. And we know that therefore we must be getting a charge separation, therefore the electric field. So electric potential might actually seem like it's a weird topic we're adding on to talk about something we already could talk about, but it's actually the most useful for circuits. So the last thing we need to discuss is where we define 0. And what I want to drive home here is that potential difference is actually the most important quantity. And you can think about that back in terms of potential energy, that we can talk about a change in potential energy, and that is independent of where you define the 0 of your potential energy to be. Again, if I drop a ball, I might measure my height relative to the floor, and I don't actually care if I'm actually standing outside on the ground or I'm on the 17th story of a building. I can actually define 0 to wherever is most convenient. The same holds true for electric potential. Here we're showing 3 capacitors, and in each case the spacing is the same. Notice that the difference in potential from the positive to negative plate is the same. Or, sorry, in this case, they're not using the total, they're just using from here to there. But if you look at the plate to plate, it goes from 100 to 0, 0 to negative 100, or positive 50 to negative 50. And again, if you look at just kind of one point in it to another, when we're on the inside, that delta V is always 50. So in each of these cases, our electric fields look the same. They point in the same direction. In each of these cases, our charge distributions would be the same. If we had a particle, like a proton that we started at this location, we let it go, it's going to go this way and end up at that location. The delta V will tell us how our potential energy has changed, and from that we can figure out how our kinetic energy has changed. So where you actually set zero, whether it is on the negative one, which is the typical choice, like in general do that, that's usually a good choice, or you can set it zero at the positive plate, which means that you do, by definition, get a negative potential at the negative one, or heck, you can set it to be zero in the center. Again, each of these might make more sense depending on how you're doing the calculation, but use this one as your default if you don't know what to do. So this is going to be interesting and something we come back to later, that even outside of a parallel plate capacitor, we can somewhat choose zero potential to be wherever we want. We're normally going to set it equal to infinity, but there's actually going to be some cases where we can't do that. So please remember, you get to set this to be zero wherever you want, which is just like setting potential energy to be zero wherever you want, since after all, potential energy is Q times electric potential.